Hello, I am Edward Berman, and I'm going to be talking to you about covariance. As an overview, I'm going to give you some context, definition, an interpretation about what it is, a helpful example, and make some connections. So for some context, we should already be familiar with this simple variance. It's the expected squared deviation of our inner variable from its mean. Mathematically, sigma squared of x is equal to the expected value of x minus mu x squared. Uh, so now we talk about covariance. So if x and y are random variables, then the covariance of x and y is equal to the expected value of x minus mu x times y minus mu y. And hopefully my tone sort of indicates that this covariance is some sort of generalization of the variance. So how should we interpret what this covariance means? We can see that it's the product of the deviation of x from its mean and y from its mean. So let's consider some cases. If the covariance of x and y is greater than 0, then we may say that if x is far from its mean, then y is far from its mean, i.e. larger values of x tend with larger values in y. Conversely, if covariance of x and y is less than 0, then larger values of x tend with smaller values in y. So that leaves the obvious question. Well, what about covariance of 0? Well, if x and y are independent, then covariance of x and y is equal to 0. But the converse is not true. Here's an example. Here you're reminded of the definition of covariance, and here's an example. This is a discrete case, but it's true for the continuous as well. Let there be three outcomes: negative 1, 1, 0, 2, and 1, 1, all of the same probability, 1/3. There's not independence here, since knowing one value tells you information about the other. For example, if you know that x is equal to 0, well, then you know that y must be 2. So also note here that mu x equals 0 and mu y equals 0. So this is 0 and this is 0. So we just have the expected value of x times y. So we can just calculate this explicitly, and we come out that it is 0. So we have come up with an example where covariance of x and y is 0 and x and y are not independent, simply by considering these three values and their probabilities. So recall from the definition of variance. See that the covariance, if we consider the covariance of x with itself, then we'll get the expected value of x minus mu x squared, which is exactly variance. So as I hinted at before, covariance is a generalization of variance for joint distribution. This relationship can be explored further in noting that the covariance of x and y can be written as e of xy minus e of x, e of y. So note here in our example problem, e of xy is 0. E of x and e of y were also 0. So we got a covariance of 0. This would have been a more straightforward, I guess not necessarily more straightforward way to calculate it, but in other problems, this is very helpful. But remember also that the variance of x and y is equal to e of x squared minus e of x squared. So we have x squared, the expected value of that, and then e of x, the quantity squared. So here, if we have covariance of x and x, this, again, it'll reduce to the variance. So we see covariance really is just a tool that allows us to generalize variance onto joint distribution. Thank you.